Chapter 2 is titled Linear Equations and Functions. In Lesson 2.1, we have quite a bit of terminology to help represent relations and functions. The definition of a relation is a mapping or pairing of input values to output values. Domain stands for the set of all input values. Typically, when we graph linear models or look at linear functions, that's the x variable. Range would then be the set of all output values. Usually what we have our equation equaling, which oftentimes is the value for y. We will focus on representing relations in a variety of ways, which include ordered pairs, creating a table, plotting points on a graph, and a mapping diagram. Consider the relation given by the following ordered pairs: -2, -3, -1, 1, 1, 3, 2, -2, and 3, 1. First, we're asked to identify domain and range. When we do so, we want to write our values in order from least to greatest. So make sure to follow that when we list these values out. To identify the domain, we're looking at all of our input values. I'm going to write capital D and then just a semicolon to identify that. My input values are all the x's, so go ahead and underline them in a certain color. Notice they're already written from least to greatest. That makes the domain super easy to write out. I use a brace, and if you just want to draw like a little squiggle line, if a brace is not like something that is easy for you to create, totally okay. From least to greatest, we have -2, -1, 1, 2, and 3. Those are all the possible input values we see in our ordered pair set. As we think about range, those are the output values. So go ahead and circle all of the numbers that represent the y coordinate, and those are all of our range options. Now, in a couple of these, we have the same number. So as we state our possible options for range, we wouldn't write numbers that repeat themselves. I notice here that they're not written in order, so we just have to kind of look through it. -3 is the smallest range value, and then I see -2. I see a 1, but I see a 1 again, so we just list it once in the range, and the range goes all the way up to +3. That's identifying the domain and range literally by just creating a list of the numbers that represent them. When asked to represent the relation in a graph, we're literally just going to plot our ordered pairs, making sure that we know the x values always count to the left or the right, and the y values count up or down. To plot -2, -3, I'll count 2 to the left and down 3 and put a point down in quadrant 3. To plot -1, 1, I'm going to count just 1 to the left and go up 1, and that puts us in quadrant 2. 1, 3, count 1 to the right, up 3. There's a point in quadrant 1. 2, -2 puts us in quadrant 4. And then 3, 1 again puts us back up in quadrant 1. That's representing the given set of ordered pair values, the relation, as a graph. The other one is a mapping diagram, and this might be new for you. Out of all the ways to represent a relation, the mapping diagram, quite honestly, is the least commonly used method, but it is an option. What we're going to do here is just kind of create an oval for our possible domain values. We're going to do another oval off to the right for our possible range values. Just like listing them over on that left-hand side in part A from least to greatest, I'm going to do that vertically in each column, or in each kind of oval. For the domain, we have -2, -1, 1, 2, and 3. That's kind of the pool of our choices. For the range, we only had -3, -2, 1, and 3. Here's what makes this a mapping diagram. We're literally going to arrow from an input to its corresponding output. That means that first order pair -2, -3, you draw an arrow to show that connection. -1 mapped over to 1, so we draw that arrow down to +1. 1 for the domain goes to +3 in the range, just kind of arrow over to that location. And then it's 2, -2, so we kind of cross over here up to -2 up at the top. And our last ordered pair in this mapping diagram would go from 3 to 1. If asked to create a mapping diagram, that's literally what it would look like. To be a little bit more specific with a relation, making it a function. A function is defined as a relation with no repetition in the domain. That's going to be a key criteria to justify your reasoning. Let's take a look at the two sets of ordered pairs on the right to define why one set is and one set is not a function. When asked to determine if a relation is a function, we literally just look at the x values, which would be their input values. Notice in this first set of ordered pairs, our domain is 2, 3, and 4. None of those values repeat, therefore it is a function. So no repetition in the domain. Super simple. That means each x value has a unique output. Over on the right, it's not the case. So on the right-hand side, if we look at our ordered pairs, I have 0 and 3, but then 3 repeats itself again, which means the same input has two different outputs. That's why this is not a function. There is repetition in the domain. It's really easy to justify this. And there you go. That would be just kind of explaining your reasoning. So I'm going to give you an opportunity to just kind of practice what I've talked about in the first part of this video by identifying the domain and range for each set of ordered pairs above. Remember to write your values from least to greatest, and we wouldn't write numbers that repeat themselves. Once you complete both of those examples for A and B, press play and we'll see how it went. How did it go? Notice for my domain in part A, I just wrote them in order 2, 3, 4, but for the range, we only had -1 and +1. Even though -1 repeats, it's still a function because that doesn't affect our input or our domain. For example, B, we only have 2 possible choices for the domain, 0 and 3, and again, only 2 possible choices for our range, -6 and 2. When looking at the sketch of a graph, we can tell if the graph represents a function by applying what's called the vertical line test. If a vertical line intersects a graph at more than one spot, the graph is not a function. Instead of having to write out vertical line test every single time, I like to abbreviate it as VLT, and that means vertical line test. We literally draw vertical lines on the graph. It's a super easy test to determine whether or not the graph represents a function. Which graph represents a function, and how do you know? Taking a look at the graph on the left, it's kind of like, it looks like it's about 10 minutes to 3 o'clock right there. If we try to represent or try to verify if it is a function, draw a vertical line. So that means a line from top to bottom. Notice on that left-hand side, I would only cross the graph at one location. If I pick another spot, test it again, only one location. Over here on the right, still one location. If you ever intersect more than one time on the given graph, then it doesn't represent a function. But this one has no issue with that. Therefore, yes, it is a function. And how do we know? It literally passes the VLT, or the vertical line test. Now, over on the right, it's pretty clear to see that that's not going to work out so well. We kind of have this curved shape from top to bottom on the right-hand side of the graph. If I draw a vertical line here, it only takes one test to verify that it crosses up here at the top and at the bottom. So unfortunately, this is not a function. And if I ask, how do you know? It does not pass or it fails the VLT. Make sure that if you're asked to explain why, that you say it either does or doesn't work for that test. Our last major focus in Lesson 2.1 is titled Function Notation. This notation is important when you have more than one equation that you're working with in a given situation. And sometimes having y equals for every equation can be a little bit cumbersome. A linear function follows the format y equals ax plus b. If you remember this template, it's called slope-intercept form for the equation of a line. A little throwback here to Algebra 1 and maybe a little bit of work in geometry. Now what's unique about this is our variable. In order for a function to be a linear function, your variable only can have an exponent of 1. And typically if it's not written there, that's what it would default to. So we don't want anything squared or to the third power or a square root or even absolute value. We can only have an x to the first power. Over on the right, let's see some examples that either are or not linear functions. Determine if the equation is linear or nonlinear. Y equals negative x squared minus 2x plus 7. So I see a linear term, which is promising. However, that first term, the negative x squared, has an exponent greater than 1. Because of that, this is called nonlinear. So literally no other x terms can be there except for an x to the first power. In example B, y equals 5x plus 8. Notice that looks very similar to the definition over on the left-hand side. In this example, that x is just plain. Technically, it's raised to the first power, and nothing else is changing that value of x other than the slope of 5, or that a value of 5. That makes this equation an example of a linear function. Our last one, y equals absolute value of 2x plus 3. This one gets a little tricky because we do see that that x value just has an exponent of 1, but the absolute value part around it is nonlinear. So make sure to write that down. Absolute value is nonlinear. So the bars on each side of the equation are what make it a nonlinear kind of setup. This is the part of the video where things get a little bit tricky. Function notation. So it said function notation at the top, but we really haven't worked with it yet. Remember what I said before, we need this notation because oftentimes we deal with more than one equation in a certain word problem or situation. If they're all y equals, that can get a little kind of tedious to work with. What we do instead is we apply function notation known as f and then parenthesis x. We'll replace the y variable with that notation. X still represents the input or our domain. This f with the x in parentheses is now our output. So it means the same thing as y, and you read it like this. F of x. That means the function of x. And so we'll first start off just by rewriting our equations in that notation, and then I'll show you how to evaluate. We're asked to rewrite the equations above in function notation. The right-hand side of each equation isn't going to change at all. This is really easy to do. We're just going to take those y values and replace them with f of x. So this is what it looks like. Instead of y equals negative x squared minus 2x plus 7, we're literally just going to write f of x equals, and then the right-hand side stays the same. Negative x squared minus 2x plus 7. That's all it is. Let's try the next one. Y equals 5x plus 8 now becomes f of x equals 5x plus 8, and that's written in function notation. For our last one, y equals 2x plus 3 in absolute value now becomes f of x equals absolute value 2x plus 3. One other thing to note for this function notation is we can use the letter f, but we can also use other ones. Like, for example, we could also say g of x. That's a different function. H of x. We could say p of x. All these types of notations represent function notation. So you might see something other than the letter f out in front, but it just means output. So you would do the same process. The last thing we're going to do is evaluate in function notation. To evaluate means you're going to plug in a value for x on each side. Then you leave the left side alone and you only simplify the right side. Let's take a look using those same definitions or those same equations up above. Evaluate each function above when x equals negative 4. So if x equals -4, wherever we see x, we literally just plug that in. Our first example, f of x means f of -4. Now, this example is the trickiest of all three of them, but I put it first because we're just going to get it over with. Negative x squared. Remember, anytime that negative is out in front, we evaluate that separately, thinking order of operations. Negative x squared, well, if x is -4, it's -4 squared. And then minus 2x, so minus 2 times -4 plus 7. Order of operations is critical on this, everybody. If we take a look at that first term, notice we have to do -4 squared. And that would give us positive 16. So -4 squared is positive 16. But the negative out in front makes that negative. Think about that for a minute. The negative out in front makes that answer negative. From there, hopefully we can navigate the rest of it. -2 times -4 becomes positive 8. And then we have our constant of 7 at the end. -16 plus 8 plus 7 would be the same as -16 plus 15, which equals -1. That's our output. To write your final answer, we literally just say f of -4 equals -1. The function has a value when x is -4 of -1. That's our output. All right, you try the next one. Plug in -4 to example B up above and see what you get. Then press play and we'll do the last example together. Did you get -12 as your output? If you substituted -4 on the right and simplify, f of -4 equals -12. All right, off to our last example and then we're done, everybody. F of -4 equals absolute value of 2 times -4 plus 3. To simplify the inside, 2 times -4 is -8 plus 3. Remember, we're still in that absolute value scenario though. -8 plus 3 is -5. And the absolute value of -5 is 5. That makes f of -4 equal to positive 5. That is our output. And that's evaluating using function notation. Up next, let's try a little practice with our CYU.